All right, so today we're going to take a look at section 5.6, which is inverse trigonometric functions, and we're going to talk about differentiation. And in order to start even talking about any of this, we've got to go back and talk a little bit about how our trig functions were defined. So in particular, you have 6 different trig functions. And we're going to look at the first, this slide's going to have the first 3, and then our next slide will have our next 3, and they're in your notes. What I want us to take a look at is in these different scenarios, what are our domain, our range, and our quadrants that we're allowed to have. So this was something that you would have done in trig probably the middle to the end of the semester. So some of the more complicated ideas. One of the issues with trigonometry is that everything repeats itself, right? So like you think about your sine curve and it has this sort of a wave pattern that keeps going. Okay, right? Like the wave that goes around the stadium, it keeps going in theory. Well, in order for a function to have an inverse, what did we talk about back in 5.3? It has to be 1-to-1. Well, trig functions in general, they're not 1-to-1, right? Because they have this repeating pattern. They do these waves, or if we're talking about tangent or cotangent or secant or cosecant, they have repeating portions of the graph. And so they're not 1-to-1. So in order to talk about there being an inverse at all, we have to restrict the portion of the graph that we look at. So let's take a look, and I'll draw the picture of sine on the board just to remind us. But sine is a wave pattern, and for the graph of sine, it actually goes through the origin, and it looks something like this. Right? So in trig, you actually learned that if you restricted the picture of sine to a certain portion of the picture, then it would in fact have this 1-to-1 feature. Do you remember the pieces that you had to restrict it to? Okay, well, that's the x, right? This is -1 and 1 here. But what about, sorry, that's the y's. What about x? 0. Okay, if I start at 0 and I go over here, which this is pi, that's a problem. Some of you said stop at pi halves. Okay, so if I restrict my domain to only look between negative pi halves and positive pi halves, I actually have a 1-to-1 function. Well, that domain is actually a domain for sine. And I'm talking about arc sine. Arc sine is the same thing as the inverse sine. So sometimes you'll see it written, instead of being written like this, you'll see it written as this. Your calculators usually write it this way. I'm not sure I've ever seen a calculator actually write arc sine. It actually writes the sign with a little -1. So it's good to know that that's the button that it's talking about. The problem with this notation is that the little -1 notation has lots of meanings for us, doesn't it? Well, we've used that notation already this semester to talk about it being the inverse of sine, which is exactly what we mean here, that little -1. But you've also had that -1 represent putting things in denominators, like exponent rules, right? Which we've also encountered this semester already. So I will tend to work with the phrase arc sine so that there isn't any question of which one we're talking about, because it has this sort of a multiple meaning idea thing going on. But when I talk about the inverse, so this one right here that's on the board is the graph of sine. So this is y equals sine x. And if I look just on this piece, my domain is from negative pi halves to pi halves, right? And my range is what? -1 to 1. But what I have on the iPad is that I actually have the inverse sign that I'm talking about. And what did we say back in the section about inverses happens when we talk about the inverse function compared to the original function? The domain and the range switch. Because that's what inverses do. Inverses switch the x and the y's. And domain corresponds to x, range corresponds to y. So if I switch them, the domain and range switch as well. So what we've actually got here is that my domain is the -1 to 1. And my range is negative pi halves to pi halves. Okay, so now I want you to think one more time way back into trig. This is way, way early into trig. Do you remember something called the unit circle? Most of you had to memorize it. Not sure that most teachers would let you get by without. So you had this sort of a circle, and it started from 0, and we went up to pi halves, and you went over here to pi, you went down here to 3 pi halves. You could also go backwards around the circle, right? So if we went backwards, this one would also be negative pi halves. This would be negative pi, and this would be negative 3 pi over 2. And we could talk about this being either 2 pi or negative 2 pi back at the positive x-axis. So thinking about this, we also have names for these quadrants. Quadrant 1, where is that? Top right. Quadrant 2 is the top left, bottom, and then this way. And at some point we talked about this idea of going counterclockwise, going around the circle, labeling this way has to do with the fact that the person who was doing this, when it was all conventionalized and whatever, was left-handed. And so they went backwards around the circle from how we would go around a clock, right, when we go clockwise. All right, so taking a look at this, which quadrants does this domain of negative pi halves to pi halves correspond to? 1 is correct, and 2. 1 and 2, because it goes from negative pi halves up to pi halves. Does everybody see that? So this domain here, from the sine function from negative pi halves to pi halves, is talking about quadrants 1 and 4. So this happens in quadrants 1 and 4. Okay, we're going to do the same processing now for arc cosine. So for cosine graph, the cosine graph did not look like this. Okay? My cosine graph, it had the same sort of an image, but it looked sort of shifted, didn't it? And so you had a graph that looked something like this instead. These markers need to be retired. They're weak. So this is the graph of cosine. And I need to restrict that graph as well so that it's 1 to 1. What are my restrictions to make the cosine graph 1 to 1? 0 to pi. So if I start at 0 and I stop over here at pi, I have a 1-to-1 graph. So that's my domain, 0 to pi. And my range is what? Negative 1 to 1. Okay, so just like on the last one, I'm doing arc cosine, so these switch. So my domain for arc cosine is the negative 1 to 1, and the range is 0 to pi. In terms of my unit circle, my quadrants, what quadrants are those? 1 and 2 this time, that's right. So they do not match with sine at all. All right, let's do tangent. Tangent does not look like a wave, does it? No. In fact, at some point somebody probably told you it looks sort of like a graph of x cubed, maybe. Has that sort of a feel to it in some respects anyway. So the graph for tangent looks something like this. And it has lots of these guys, right? We can keep repeating this pattern as far out to the left and right as we want. And as we do, you notice that if we keep doing this, then it's not 1 to 1. But had I stopped with the very first curve that I drew in the middle, it would have been, right? So do you remember where these stop? Where does that break apart? Somebody said it. It's negative pi halves to pi halves. And the reason that happens is because the period for a tangent curve is actually pi instead of 2 pi like it is for sines and cosines. Sines and cosines repeat a full 2 pi later, but for tangent and cotangent, it's a period of pi. So we actually get a repeating pattern every, this is negative pi halves to pi halves. So every pi units, it will repeat the pattern. What's the range for this one? Yeah, that's different. In fact, you know what? I even wrote this wrong. These are not brackets. That negative pi halves to pi halves are parentheses because I've got asymptotes. And then this one's negative infinity, infinity, as you said, for range. Okay, so let's go back into the arc tangent now. So if I'm doing the arc tangent, the domain and range switch. So my range is actually negative infinity to infinity on this one. Sorry, my domain is actually negative infinity to infinity on this one, right? And my range is negative pi halves to pi halves. What What quadrants correspond to that negative pi halves to pi halves? 1 and 4. Okay, we have 3 more. I'm not going to go into quite so much depth on the next one because the image is almost the same. When you're doing cotangent, it shifts it a little bit, right? It actually ends up being between 0 and pi, and it goes downhill instead of being going uphill. But the domain is still the negative infinity to infinity. Just like for a tangent, you've got the same sort of an image going on, but it looks sort of upside down. And then the range goes from 0 to pi. Again, with the same thing with those asymptotes. And what quadrants are 0 and pi? 1 and 2. All right, let me talk about secant, and then cosecant will be very similar. So I've still got the graph on the board right now of cosine. This graph right here of cosine, which is so light you probably can't see it, but we're going to try it darker and see if it helps. The graph of cosine is right here. Agreed? So if I were, I'll draw a little bit more of it. If I were to draw the graph of secant, what happens is that everywhere I had an x-intercept becomes an asymptote. Remember I doing this in graphing and trig? Some of your favorite sections. I just know it. Because that was the first thing you did, is you turn all the x-intercepts into asymptotes. And then the next piece is that you took every maximum and you made it a minimum, and this red that I'm drawing on the board now is the part that's actually your graph. So it looks like that. So the red part only is the graph of secant, right? Again, not 1 to 1, okay? But if we restrict it the same way that we restricted the original one, that is the cosine graph, it is 1 to 1, isn't it? Yes, it is. So we're going to restrict that in the same way. So if I restrict that, the domain that I'm looking at on the board is actually still 0 to pi, right? So that's the range for the inverse up here. So, and it's a little trickier. It's not exactly 0 to pi, so let me pause on that. I'll come back to that in a moment, but it's sort of 0 to pi. And then the range is actually the bottom half, the bottom part of the graph, so it's from -1 down, right? And it's from +1 up. Do you guys see that? And when we write that in interval notation, we usually start at the minimum value and we go up. So we'd say we go from negative infinity up to -1. So this is the one where I don't have enough space in what I've got on my screen, but I think you guys do. This is negative infinity to -1. And I have to put a parenthesis because I can't actually equal that negative. I'm sorry, no I don't. I take that back. A bracket. I can equal the -1 value. And then I'm going to do a union, and I'm going to go from 1 to infinity. So I've got a gap between -1 and 1. As you can see, the graph of secant, there aren't any secant values. There's cosine values, but there aren't secant values. Now, the range has an issue. It's not really 0 to pi. What is the issue between 0 and pi? There's an asymptote at pi over 2. So the way that your book writes this isn't how I would write this, is that they will tell you right here that y cannot equal pi halves. If I were to write this, I would actually do it much like I did the domain. I would write 0 to pi halves, and I put those in parentheses with a union, and then I would put pi halves to pi. Okay, that would be another way to express that. But 0 to pi, what quadrants are those? 1 and 2, which I see I've got a typo on the board. Nobody wanted to say, hey, you said it right and wrote it wrong. We'll fix it. This was 1 and 2 up here as well. Sorry. Yeah, you guys said it right, but I wrote it wrong. Okay, cosecant is going to have the same flair to it as secant did, right? But it relates back to sine. So if I were to draw the sine graph on the board again, and we were to draw the cosecant graph according to it, it would have the same domain and range. It would have the same range as the original one did, but it would not have the center piece. So if I went and did the range on this piece, I would go from negative pi halves to pi halves. And I would have to exclude the value 0 halfway between because I have an asymptote there. If I were to look at the domain for that, the domain would have the same feel as well as the secant graph did. It would be negative infinity to -1, union 1 to infinity. And if you're taking a look at that quadrant, what quadrants correspond in negative pi halves to pi halves? 1 and 4. So it is very interesting to look and sort of make some comparisons. You notice that sine and cosecant and what else have the same quadrants? Tangent. So sine, cosecant, and tangent are all quadrants 1 and 4. Whereas cosine, its reciprocal secant, and cotangent have the quadrants 1 and 2, right? So there's some interesting things there. All right, so I want us to look at some different trig features first. This is the same way we've started every other section in Chapter 5. We go back and we look a little bit at the algebra. This time we're going back a little at the trig. And so I want to talk about arc sine. So this says arc sine of 1/2. And so if you do not have your unit circle any longer, it would probably be a good idea to go find one. And you can just Google unit circle. There will be an image pop up. It'll have all of the angles and all of the coordinates and everything in there for you, okay? It's something you should memorize again. And if you don't memorize it, you should probably have it written down so that you can reference it very frequently, because you're going to need it in this section and a few others as well, okay? So taking a look at this one, the way that we're dealing with this is that this question basically is telling you, oops, well that'll work. Let me use red. That this is equal to some angle. All right? Because the equivalent to this, and I didn't point it out strongly, but let me go back and make mention of it. Y equals the arc sine of x is defined to be if and only if the sine of y equals x. So notice here, this is sine. Its angle inside is y, isn't it? That's the angle that equals the arc sine of x. That's the relationship. So when you're asked to find the arc sine of something, you're asked to find an angle. You're asked, what angle gives me a sine value of whatever? So in this case, I can rewrite this to think about it. I'm being asked what angle gives me a sine value of 1/2. But the kicker is that I can only work within the quadrants I'm allowed to work. For sine, which quadrants am I allowed to work in? 1 and 4. There are lots of other answers that I could give, lots of other angle measures. I could go around the circle as many times as I want, either direction, and I can find all kinds of answers. But the answers I'm asked to find are going to be answers that are in quadrants 1 and 4, because it started out asking the question in terms of arc sine. Here's the other thing. Some of you think in degrees. Raise your hand if that's you. Who thinks in degrees? Yeah, most of you do. I do too a lot of times. Your answer at the very end, I'm fine if you put it in degrees in there somewhere, but your answer at the very end? Radians. And the reason it needs to be in radians is because when you defined derivatives and antiderivatives for sines and cosines and everything else, you were working in real numbers. Real numbers are radians, or I should say radians are real numbers. Degrees are not. All right, they're measuring in a different way. So once we get into the calculus part of this, and you've hit on it already some in Calc 1, you have to be working in real numbers and radians. All right, so here's the first thing. Does anybody remember what angle measure gives you a sine of 1/2? 30 degrees. You're close, Janet, which is pi over 6. Yeah. So the answer is actually pi over 6. So if you have your unit circle, a few things to remember about your unit circle is if you're in quadrant 1, all of the signs are positive, right? Sine, cosine, tangent, secant, cosine, everything has a positive sign. If you're in quadrant 2, some of your values are negative, right? So let's remember for ourselves. So over here, they're all positive in quadrant 1. What's negative in quadrant 2? The x values, right? So if you're on the left-hand side of the graph, your x values are negative. So which of your functions corresponds to x values? Sine, cosine, tangent. It's cosine. So over here, your cosine value is negative. Everything else is positive still, right? Well, I should say your sine value is positive and your tangent value is a ratio, actually. So your tangent value would also be negative because it relates x and y together. So tangent is negative. I guess I'm sort of identifying this backwards of how I normally do. I usually tell you what's positive. Now I'm telling you what's negative. That's okay. It's equivalent. How about down here in quadrant 4? I don't even need to talk about quadrant 3, actually, today. Why? None of my quadrants had quadrant 3 as an option, so I'm going to ignore it entirely. Down here in quadrant 4, since I've already started out talking about what's negative in quadrant 4? sine, and tangent. So these are both negative down here. And to be honest, the ones where it matters are sine and tangent down here in quadrant 4 and cosine up here in quadrant 2. I wrote it, but it's really not helpful for our discussion today. Why? Because tangent's only going to be working in quadrants 1 and 4 as well. Okay? So when I was told that my sine value is 1/2, and I know I'm in quadrants 1 or 4, the fact that it was a positive 1/2 put me in quadrant 1. Okay? So if you're looking on your unit circle, you're thinking about your unit circle, you should only think about quadrant 1 at that point. Here's another reminder. So if you've got an x, y coordinate and you're looking at your unit circle, which one is sine? Sine is y, and then cosine is x. So if you're looking within quadrant 1 or whichever quadrant and you're identifying sine, you're looking at the y value. You want the y value to be equal to 1/2. And the y value in this case is 1/2 when sine is, or when the angle is going to be 30 degrees or pi/6. Okay, so that's trig in a nutshell, or at least a little bit of the unit circle in a nutshell. If you're not remembering pieces of it, you've got to get your hands on a unit circle. Okay. All right, let's do another one. This one is arc secant. Now, I should make mention of the fact that if you use your calculator and you put that sine inverse of 1/2, it's going to tell you 30 degrees or pi/6, depending on how your answer is. So I say it's going to tell you that. It sort of is. If you have it in degree mode, it's going to tell you 30 degrees. If you have it in radian mode, of course, your answer does not show up as pi/6. It's going to say some weird-looking decimal, right, that you would have to hopefully recognize that might be pi/6. The problem with that reasoning of just can I grab my calculator to look at it is it doesn't work especially well for this because you do not have a secant or an arc secant button in your calculator. You have ways to manipulate this, to change it into something your calculator can understand, but you can't enter this in directly, whereas you could have on problem number 1. So you need to be able to manipulate a little bit with this to think about that. So I'm going to start with the same way I did last time. We're going to set this equal to theta, and I'm going to rewrite this with what it's actually asking me. It's telling me that the secant of theta is equal to negative square root 2. I don't know about you guys, but I don't really think in terms of secant. I think better in terms of sines and cosines. So my inclination is, let's change this thing into something I can think about it in a little bit easier. And cosine would be that thing, because secant and cosine are reciprocals, right? So if I change secant to cosine, in effect, I have taken the reciprocal on the left-hand side, right? What is the reciprocal then going to look like on the right-hand side? 1 over negative square root 2. Some unit circles you see online will have it expressed like this. Most don't. Most of them will rationalize the denominator. So you went through great feats to rationalize denominators in several classes along the way. Do you remember how to rationalize this denominator? Yeah, you multiply the square root 2 on the bottom and top. In fact, looking at this, you might have already recognized before I even said that this is equivalent to the negative square root 2 over 2. If not, you do now. All right, so this, first of all, has a cosine value that's negative. Which quadrant would that be in? 2. So you're looking at your unit circle, you're thinking about your unit circle, you are over here. And you're looking for the angle measure that gives you a square root 2 over 2. Do you remember which angle measures gave you square root 2 over 2's? They're always the 45s, right? So if you're in quadrant 1, that's actually this 45. In quadrant 2, it's 45 over here, but of course that's not really 45, it's 135. So in terms of degrees, this would be 135 degrees. But we're not working in degrees, we're working in radians. So in radians, what is that? Good, 3 pi over 4. Great. So far, so good? Okay, let's look at C, the third one here, number 3. What's different about C than the ones before? I've got a sine of an arctangent, right? What's even more different, and you might not recognize this at the first here, is that if you were just told, like if I covered up the sine at the beginning here, and I just said arctangent of 3 over 4, 3 over 4 is not on your unit circle. So this is not something the unit circle is going to be helpful for you to use. Okay? So we have to think about what is going to be helpful. And what's the other big idea besides unit circles and graphs and identities from trig? Triangles. They were all over the place. Do you remember them? We're going to use triangles, and specifically, do you remember what kind of triangles, Jordan? Right triangles. So we're going to use a right triangle for this. So let me show you. We're going to draw ourselves a right triangle. Now, one thing we can talk about immediately, though, is that this arctangent value is 3. This is the arctangent of 3 over 4. So what quadrant am I in? 1, because it's positive, right? Tangent values are positive in quadrant 1. So I'm going to draw my triangle as though it were in quadrant 1. Okay, so here is a right triangle. Remember, the right triangles always become right angles on the x-axis when you're drawing them out. The angle here in the middle is theta. We're always using the central angle. And this theta is this quantity. Okay? And so if I think about just the part that I've sort of marked over here in blue, I can rewrite it just like I did on the previous 2 examples. The tangent of theta equals 3 over 4. Now in terms of triangles, what do you remember about tangents and sides of triangles? It's opposite over adjacent. My screen's not showing up for you guys at the moment, so. Okay, so the tangent in relation to a triangle is the opposite over adjacent. So with my angle theta being here in the middle, the opposite would be that vertical piece, and the adjacent would be this horizontal piece. So far, so good? So I picked this one on purpose because I want to show you how the problem works without it being complicated. This is probably a triangle you recognize. What's the third side? It's 5. And if you didn't recognize it right off the bat, if it weren't a 3 and a 4, say it were a 3 and a 2, what would you do? The Pythagorean theorem. So you can use the Pythagorean theorem to find that third side. All right, so what is helpful about this? Well, what's helpful is that I've created a triangle based on what's inside the parentheses, right? But what I'm actually asked to find is I want to find the sine of that angle, because I called what's in the parentheses theta. So now looking at my triangle, what is the sine of the angle theta in this triangle? It's 3 over 5. And I never needed to know what the angle was to do any of that, did I? So that's really good news, because finding that angle would have been really ugly. I would have had to use the calculator. The calculator would have had to have given me an approximation, and then I would have probably had some measure of error in my final answer because I approximated along the way. And there's no need to approximate. So this is actually 3 over 5. Okay, any question about that process? Okay, we're going to do another one that's like it then. All right, so we have the tangent of the arc sine of negative 5 over 6. So issue number 1 is that I'm going to recognize that I need to use triangles. Why? What about this says, I need a triangle, I need a triangle? I've got the 5 pi over, or the 5 over 6, that's part of it. And then what else did you say?
It was in parentheses as a tangent.
Yeah, we've actually got 2 trig functions. One that's a trig function and one that's an inverse, and we're trying to operate with both of them. Okay, so those 2 pieces together tell me triangles are going to be helpful here. Now, I need to figure out what quadrant I'm in. What quadrant am I in? 4. Why 4? Because the sign's negative, exactly. Okay, so I'm going to draw this picture. I'm going to draw it down here in quadrant 4. Okay, my picture is a sketch. It's not meant to show actual lengths. Central angle, always the one in the middle. That's this theta, and I'm going to call this theta. So I'm going to think about this as though it says the sine of theta equals negative 5 over 6. All right, so my angle theta is right there. Where am I going to put that negative 5 and that 6? Or the 5 and the negative 6? Where are these things going to go? Opposite. So the opposite is the 5. The hypotenuse is the 6. And then where will the negative go? It will go on the 5 because that's actually a negative y distance, right? That distance down is considered a negative y coordinate. Now on this one, I don't have a 3, 4, 5 triangle, so I'm actually going to use the Pythagorean theorem. Okay? So this side right here, call it a, b, c, q, x, whatever you'd like. And we're going to have a squared plus negative 5 squared, hang on, equals 6 squared. All right, so what's 5 squared? 25, and so is negative 5 squared. What's 6 squared?
36.
36. What's my next step? Subtract my 25 So a squared is going to equal 11, and then a would actually equal the square root of 11. Technically, it's actually plus or minus. We do have to make the decision based on the location of a. Is this a positive square root 11 or negative square root 11?
Positive.
It's positive because it's on the x-axis, right? All right, so I've got square root 11 on the top side of this triangle now. Now I'm supposed to be finding the tangent of theta based on this picture of the triangle that's not complete. What is the tangent based on this picture? Negative 5 over square root 11 and rationalize. That's right. You don't get to leave it that way. It rationalizes in the same way, the same manner as the last one we looked at. So this would actually be negative 5 square roots of 11 over 11. Any questions on that one? Okay. We're going to do one more. It's got a variation of it. What's different about this one than the last one? There's a letter in there. There is not a number at all. And it actually doesn't operate any differently. I mean, we don't do the process any differently. It's just that we're going to have an answer with an x in it when we're done. Okay? So because I don't have any other reason to do it differently, that is, I don't know what the value of x is, I can draw it in quadrant 1, and everything will work out okay. So that's actually kind of nice. I don't have to worry about what quadrant. So if I'm dealing with a variable, I can draw it in quadrant 1. Now, this says secant. So this is going to say that the secant of the secant of theta equals x. So in terms of a triangle, here's the theta. Secant is related to cosine, and cosine would be, it would be adjacent over hypotenuse, right? So the adjacent would be this piece down here on the bottom, the horizontal distance, and the hypotenuse is along the side. And so instead of putting in this as x on the bottom and 1, I'm going to put it in reversed, right? So this would be the 1 and the x. The secant, so in fact, let me write it down the way that you mentioned it. I could also think of this as being the cosine is 1 over x, if that's helpful. That's an equivalent value, okay? But I'm asked to find out something about sine, and sine involves the opposite side, and I don't have any value over here on the opposite side yet, so I'm going to call it a b. I want to find out what b is in terms of the other two sides, that is, in terms of 1's and x's. So it's Pythagorean theorem, just like before. So we're going to have x squared, let me get it right, 1 squared plus b squared equals x squared. And our goal is to solve this for b. I mean, I want to know what is b in terms of x. So, well, this is 1 plus b squared equals x squared. So b squared is equal to x squared minus 1. And then I square root. So b equals the square root of x squared minus 1. So far, so good? So then what's the sine value in this triangle of theta? Make sense? Good. All right. I am going to fill in the next set here of derivatives, and then we're going to pause. Okay? These are derivatives of inverse functions. If you have your derivative sheet with you, you can put them in both places at the same time. They are problems, they're parts 19 through 24, the last 6 of them that are on there. And we're going to need these when we pick up with this lesson next time. We're going to look at the derivatives of the inverse functions. So when you have a function that's arc sine of x, its derivative, all of these, by the way, are going to look somewhat similar to one another, is going to be 1 over the square root of 1 minus x squared. And let me make a comment. You're going to see radicals in the denominators of all these. The reason they're not rationalized is because depending on what x is would determine whether you'd have to actually rationalize something. X is a variable, so we don't have to rationalize exponent, or we don't have to rationalize radicals with exponent. I can't talk. We don't have to rationalize radicals with variables in them. Okay, so that is perfectly fine that it's left in the denominator here. All right, cosine looks very much like the derivative of arc cosine looks very much like the derivative of arc sine, except that it's negative of that value. So that's pretty cool. Once you know one, the other one's just the negation of it. Tangent is easier to work with because there aren't any radicals. If you actually took a ratio of the above ones, you'd actually get this is going to be 1 over 1 plus x squared. That's arctangent's derivative. Arc cotangent's derivative looks like arctangent, but what do you think it might have? Yeah, it has a negative. So it's handy dandy. And then secant and cosecant are the ugly looking ones. So the derivative for secant is 1 over, you've got the absolute value of x, and then you've got the square root of x squared minus 1. And for the cosecant, what do you think is going to happen?
Negative.
It's negative. I know. That's right. So we just have the exact same piece as secant, but it's got a negative in there on top. So when we pick up next time, we just have 3 more examples. It won't take us too long. We will finish it and the next section, but we will look through finding derivatives using those new rules. Okay?